Hello. Hello. Okay, let's start with this EM algorithm. So as I was telling that there could be a situation when you have a partially observed data. Then is that case? Then can we do anything better in that case? Hello, are you there? Am I audible? Okay, so when the data is partially observed, let's take an example just to understand what it is. For an example, somebody gives you X. Somebody gives you X, and these X are like this. This is one X. This is second X. So these are the X values of X that you know. That you know means somebody comes and gives you some different values of X. So these are the different X's that you got. And now along with the information of this X, he is telling you that see, I got these X, but these X's are generated from two different Gaussian distributions. For an example, if you have only one Gaussian distribution and you have to generate these X's from this only Gaussian normal distribution, then the probability is high here. So that the likely that you get these X's are more than you get these X's, because the density is less here. So the probability distribution, according to this probability distribution, the density of getting X is quite high here. You can get lot of X's here, but very less here, because the probability of these X's is very less. So if you want to generate the X's from or data from this normal distribution, then the data will be like this. It is quite dense here. For an example, this is 1, so 1.1, 1.2, 1.3, 1.9. You can get this kind of data from this normal distribution. But if somebody comes and tell you that this data is generated from two different Gaussian distribution, and this is the data, then again, because this is a normal distribution, this is a first normal distribution, this is a second normal distribution, then the value of getting X's are quite high here, because it is quite high near to the mean of the second normal distribution, and again very less here, because the probability of getting these X's are very less according to this normal distribution, right? So this is the case, that some came and give you data that these are the X's, but these X's are generated from two different Gaussian distributions. So each X is generated by a mixture of k Gaussian distribution. Here, k, in our case, I am taking an example of two Gaussian distribution, and we don't know the mean of those Gaussian distribution. That is the thing that we have to focus on. So here my given data set could be of what type? Could be of what type? I'm just so it could be of x1, the xi. What could be my data? What is my data? And there could be two other variables also, z1 and z2. Let's say z1 is saying that if this xi is generated from first normal distribution, in that case this could be 1. And if this xi is generated from the second normal distribution, then this is 1, this is 0. So it is one of the other. If xi is generated from z1, then this is 1 and this is 0. If xi is generated from z2, then z2 is 1 and z1 is 0. So there could be my actual data set should be in this form, where the data x is given, and along with this x, I also get the information from which distribution it is generated, from the first normal distribution or the second normal distribution. But right now, what I know only, I know only this x. I don't know what is z1 and z2, right? So this is the only thing I know, and so in this case, this data is partially observed. Partially observed means I know the only value of x. I don't know the value of z1 and z2, right? Can we estimate the z value, z1 or z2, using x only? So I know the value of x. Can we estimate the value of z1 and z2? Let's see what we can do here. So all these things are written here. So each xi is generated by a mixture of k Gaussian distribution, unknown means. We don't know the mean of these Gaussian distribution, and don't know which instance xi was generated by which Gaussian, right? So which I also don't know which xi is generated, which this xi is generated by which Gaussian. So we know, can we come up with some means corresponding to this normal distribution? For example, in my case, let's say mu1 and mu2. Mu1 and mu2. Mu1 is corresponding to the mean of first normal distribution. Mu2 corresponds to the mean of the second normal distribution. So can we can we come up with some mu1 and mu2 given the given the x? So let's see what we can do in that. And this is the same thing what I told you. Think of the full description of the instance. For example, this is the whole data set y that can have x1, sorry, that can have x and z1 and z2. So zi1 means for the ith value, what is the value of z1? For the ith example, what is the value of z2? So zi1, zi2, xi. Zij is unobservable. We don't know what is the value of Zij here. I hope this is very clear now, what is the problem now. So can we estimate the value of mu1 and mu2? So this is how we go through this algorithm. Let's assume that there is some mean. So for example, this is the case. This is my first normal distribution. This is my some normal distribution. And at random, let's say these are the two mu1 and mu2. So this is the mean of first mu1 and this is the mean of mu2. Though they are here. Actually they are here. My God. Actually they are here. But in the beginning or at the initial stage, I just assume some mu1 and mu2 at random. Now, what I will do, I will calculate the expected value of Zij. What is expected value of Zij means? On an average, given the value of x, what is the probability that it belongs to first normal distribution? Or given x, what is the probability or what is the expected value that it belongs to the second normal distribution? So here Zij, I told you that Zi is 1, where Z1 is 1 when it belongs to first normal distribution, and Z2 is 1 when x belongs to second normal distribution. So now we have to calculate the expected value. So what we are just saying here, whatever the mean I have assumed, I just take that mean only. Whatever the mean I assumed, I just take that mean only. And if I assume these two means, then the normal distribution could be like this, right? Related to these means. Using these means, I will calculate the probability of x, what I have observed. So because you know the formula of Gaussian normal distribution, right? This is the probability to normal distribution formula. I know the mean, whatever I assumed in for mu1. Let's say mu j is mu1 here. So I'm calculating the value of here, expected value of, let's say, given the ith value of x, what is the probability or what is the expected value that it belongs to the first normal distribution. So in that case, this is mu1. This is mu1. So I just put the value of x. For example, my x belongs to here. Let's say my x belongs to here. So the probability in this case, when I assume this mu1 is this. Similarly, I calculate the probability of this same x for mu2. This is mu2, right? In that case, just switching the color. So this is mu2. Oh my god. So this is mu2, right? This is mu2. So this probability will go like this. So this is x again. So when I calculate the probability of this x related to this second mu, I got this value. So from first mean I got this value, from second mean I got this value. I will normalize these two distributions. For example, from here I get 0.8, from here I get 0.0, let's say 0.1. So the probability of x belonging to first normal distribution, let's say it is 0.8. Whatever I assumed mu1, mu2 according to that. And the probability that x belongs to mu2 or second normal distribution is 0.1, right? Now what I will do, I just normalize it. I normalize it means 0.8 divided by 0.8 plus 0.1 and 0.1 divided by 0.8 plus 0.1. So this is normalization. It is nothing but it is saying at what out of 100 what is that this belongs to mu1, and out of 100 what is this belongs to mu2. It gives me something out of 100 in means of probability or in means of expected value. Now I know the expected value using these mu1s and mu2 for every x. Like, so for this x, let's say I get the probability or expected value that this belongs to 0.9 and this belongs to 0.1. For x2, I get the value of this belongs to 0.3 and this belongs to 0.7. For x3, let's say I will get the value of 0.4 and 0.6. Likewise, I get this lot of values. Now this is my in expected maximization. This is the E step. I am calculating the expected value of an unobserved variable from the observed variables. I want to repeat this statement for your sake and for clear understanding. In expected maximization algorithm, there are two steps. First, the E step and M step. E stands for expected and M for maximization. So in this example, in E step, I know the values of x. For every value of x, I am just finding out the expected value of that x. I am trying to find out the expected value of normal belongingness of that given observed variable to the normal distribution. For example, here x1 is given. What is the expected value that it belongs to the first normal distribution? What is the expected value that it belongs to the second normal distribution? I will do this thing for every given x. Now, after what is the output of this E step? The output of this E step is that for every observed variable, because of every observed variable, I have some expected value of unobserved variables. Now in M step, I want to maximize this probability. Maximize this probability, you can understand this step like this. For an example, somebody give you these points that these points are generated from single normal distribution or a normal distribution. What is the mean of it? I proved you this thing that the maximum likelihood estimation of the mean is that you add all these variables, you add all these xi's and divide by the number of xi's. How many xi's are there? Like for example, there are 100. So you divide these all xi's and divide by 100. So that's how you are calculating the maximum likelihood in that for normal distribution. If you remember, we did this for linear models. In linear models, we find out what is the maximum likelihood of variance and mean. In mean, we are adding all the x's and divided by the number of the variables. Now this is little different from this situation. Now we are calculating the maximum likelihood using the expected values. So this is my xi. I am multiplying this xi by my expected value of mu I. For example, if you come here, I am doing what? X1 multiply by 0.9 plus x2 multiply by 0.3 plus x3 multiply by 0.4. Okay, multiply. This is multiply. And divide it by expected values 0.9 plus 0.3 plus 0.4. So this is that formula what is doing. So when you calculate the expected value of Z1 and Z2, in maximization step you are just trying to find out the maximum likelihood of the mu. What is the maximum likelihood of the mu? So the formula is that you have to do the weighted sum of it, because the expectation is in the terms of a probability. Then now you have to do the weighted sum. So you are taking the value of x, you are multiplying it to the expected value, because what is the weight that it belongs to mu1 and what is the weight it belongs to mu2. If you are calculating the maximum likelihood for mu1, then if x is having more weight towards mu1, for example this column is having more weight for some particular values of xi's, then it will give the maximum likelihood for first mu1. Similarly, you do this for mu1 and mu2. Now in this step, for an example, if you have taken the value mu1 in beginning 5 and mu2 equals to 7, after this maximization step, this mu will get updated, and it may converge towards, for example, mu1 converge towards this direction and mu2 converge towards this direction. And now this, let's say this is 3, and let's say this is mu1 is now 3 and mu2 is, let's say, 9. You will take these mu1 and mu2 new values and repeat this process again until your value mu1 and mu2 will not get changed in the iterations. For an example, in the third step, you will get this value of mu1 equals to 3.003 and mu2 equals to 9.001. So here you can see that there is a very little change. It means your algorithm has already converged it, and the final expected maximization values of these unobserved variables are 3.003 and 9.001. That's how you can take this expected maximization. It is the same thing that I just explained it in the terms of I want you to understand the intuition behind it. So I did not go through this all those complex notations, and for your sake I just made it like this, and you should understand it and try to read it from the book. But from the exam perspective, I don't expect other knowledge from this lecture. Right. So let's quickly come to the second part of this bias variance decomposition. So bias variance decomposition. Okay. Should you wait? So this is the same thing that I told you, right? At first you take some values of h0, randomly take some value h0, and using those values which you have taken initially, just calculate that with some expected value. Now using those expected values, calculate the maximum likelihood value. Calculated the maximum likelihood value of the data that you are increasing, given the hypothesis or given the mu1 mu2 you have taken, the current values of unobserved variable or hypothesis, and the observed variables. So X is observed and HT are unobserved. Given these two things, you are maximizing this expression. What is the probability that you can maximize the probability of a data? Y. If you remember, Y is nothing but the X and Z's. It's a union of X and Z's. So, sorry, X and Z. What is X and Z? So you're maximizing this probability. So you are doing the same thing. So bias variance decomposition. Small E out, good approximation of F out of sample. In short, what we have is in curve learning or linear models, what we are trying to do, we had given some examples, and from those examples we were trying to learn what is the hypothesis or what is the true function. So our main motive when we learn the true function is that the approximation out of sample, or the approximations means the prediction on unseen data should be having a very less error, must having a very less error. It means that E out means error for those variables which were not used in training. E out means the error for those variables which were not used in training. Our motive is to make that error less when we are approximating some function using some data, right? So for an example, this is the data that is given to you and you are approximating some function. So somebody comes to you and give you this function. Right now you can see, or let's say somebody comes and give you this function. So this is the function, but now somebody comes and this was a true function. This was a true function. So now, because you come up with this function, and this was a true function. Now some gives you the value of X. So this should be the expected value from the true function, but what your function is giving you, this function is giving you this value. So the error is very large. So the motive is to get the error less on the unseen data. And this is nothing but the case of overfitting and underfitting. For more complex H. If you take a more complex H, means to higher order polynomial, then you could fit the data, training data very well, and you have a better chance to get the probability. You will have a better chance to get the function near to the true variable. But it may be possible that if you have a less data, then you can overfit the data. And if less complex H is there, if you are considering low order polynomial or hypothesis, then there is a better chances of generalization. Better chances of generalization means whatever the error you are getting on training, you will not get much differ error from the unseen data or the test data also. That error that you are getting from the training data set is also equal to the error you are getting from the test data set, or approximately near to. That is called a generalization, good generalization. But bad generalization is when you get a very less error in the training data and when you get a very large error on the test data. So what is bias variance? Bias variance means analysis help us to quantify E out, means to say error outside or error on the unseen data. We can quantify sometimes if we want to evaluate or if we want to do analysis, like what are the factors that are affecting my error outside. I just want to clear again that E out means the error on the unseen data. I hope that you understand this. So my ultimate motive is to do some analysis and try to find out what are the factors that are affecting that error E out. So how much the average function we would learn from the different data sets deviated from the true target functions. So bias variance analysis help us to understand. For an example, this point is important. This point is important. So for an example, this was a true function that you were trying to learn, right? And this was of order 3. This was of order 3. This was of order 3. Let's say order 3. but you have used your hypothesis set, that is constant model or linear model. Constant means this, and linear means it's a line. But if you used your hypothesis set that is not equal, that is not capable to represent this true function. For an example, your true function is of order 3, but you are using of order 1. You are using the hypothesis of order 1 to learn this function of order 3. It means you are using a line to learn this function. You can see that whatever you do, you can never learn this function perfectly, because the data set you are the hypothesis set you are using is not capable enough to represent this true function. So I just read it, this sentence: how much the average function we would learn from the different data set deviated from the true target function. On an average, I will clear this term. What is do you mean by on an average? On an average, when you learn the function from different data sets, how much it is deviated from true data set. For an example, this is one data set, you learn it, and the other data set is this from the true function. The third data set is this, and these two data sets you learn a line this. By those two data sets you learn a line this, and from these two data sets you learn a line this. So there, every time you change the data set, you learn a different hypothesis. On an average, how much it is deviated from the true data set. This first point is it's telling you this. I will clear this point very clearly in the next few slides, if you don't get confused here. And the second point is how much are the variations in the final hypothesis. I understand it. Okay. So bias variance decomposition of out of sample error. Out of sample means error that error means that the error which the data set was not used in training is based on square error measurements. What I'm trying to say that we will try to show that we will try to show bias variance decomposition using this squared error formula. If you remember, what is a squared error formula was that you have some hypothesis and you have some true function. You had some true function and you had some true hypothesis. So how much your true function value, for example, for this x, this is the value of true function, and this is the hypothesis, and for this hypothesis this is the value of hx. So how much these are different? And again, for true function, this is the value fx, this is the value of fx, and this is the value of hx. So this is the value of hx. So how much this is different? We were adding these errors, right? And we were taking the sum of these. These were the square. We were taking the sum of these in linear regression or linear models. We learned that. So this was my hypothesis which I learned, and that was my true function. I was trying to quantify the error, how much good my hypothesis was by doing this sum of square errors. So I was doing this. So here in this representation, how you can read it here, this G you can assume H only, right? This is nothing but a hypothesis. G is a hypothesis, notation for hypothesis. So in previous lot of lectures, I always use capital H for hypothesis space. Like these are the different hypothesis space which you can learn, and whatever the hypothesis learned from this space, I was representing by H like this. For an example, the hypothesis space consists of lines in 2D plane, right? For the example, this hypothesis is consisting a line in 2D plane, then your H belongs to any of the line which is fitting the data most accurately among all like H map. So this G is nothing but H. And what this D is saying, let's understand this. This is my, let's say, my true function. I don't know this true function, right? I don't know this true function, and somebody gives me a data set. Somebody gives me a data set and asks me to find out the line which can fit this data. So I fit this line using this data. And somebody changed the data set now. Somebody changed the data set and he gives me these 2 points now and asks me to find out which is the best line that is fitting. Because I don't know the true function, I have only a data set, and this time I have this data set, I am fitting the line to this, and this is the best line that I can get from this data. So every time I change the data set, my hypothesis will get changed. I hope you go at this point. So this G is saying the hypothesis, and D is saying corresponding to a given data set. Every time you change the data set, you whatever you learn, you learn, that hypothesis will get changed. For example, in this case, your capital H was all the lines in 2D planes, all the lines in 2D planes, right? Any kind of line that you can draw in 2D plane. Now this is the hypothesis set. Somebody comes and gives you a data. From all these H, you will get this best line which is fitting this data. Let's say these 2 points x1 and x2, you are mentioning it by d1. So x1 and x2. Now next time somebody changes this data set and gives you x3 and x4. So now your data set point is x3 and x4. You will get this line. So every time you change the data set, your hypothesis will get changed. If at a time you get all the data, then you will have the best line. But this would never be a case. Because if you will get all the data set, all the data, then there is no need to learn anything. Learning is because only you have some data, and you want to predict for future, for unseen data. Like so, in this GD, this G corresponding to hypothesis and D corresponding to the given data set. Every time you change the data set, your hypothesis will get changed. And what this thing is saying here, this is saying corresponding to the data set, whatever the values you are getting from the hypothesis, it is calculating the error from this hypothesis. And expected value of x means on an average, what is the expected value, or what is the expected error for a given x, right? So let's understand it more clearly from this expression. Right. So somebody is asking, sir, same kind of things we studied in the second lecture, right? We studied the same things. What is fx again? Ashish, I think this is the true function. I shouldn't repeat it again and again, but it is already. I haven't shared anything new to this lecture right now. So fx is nothing but a true function. For example, in this case, this is a true function that, and I generated some data from this true function, but I don't know. So in general, we don't know what is a true function. So true function, when we don't know the true function, we try to approximate it from the given data. So if this is the given data and I'm trying to approximate using a line, so this is what we am trying to approximate it. So this is fx here, this sine function, and this line is a hx here. And when I change the data set, my hypothesis will get changed. Okay, I don't have to repeat it again and again. Now come to this point. Come to this point. What is the expected value? This is E out for the expected value when for X. What is the expected value for in respect to the data? Now, let's say I have a population of 100 examples, and I can draw 2 examples at a time. So how many different data set I can form? Let's say I can form 100 C2. I can make these in the many different data sets, right? Now, what is the expected value? What is the expected error on all these data sets at a time? So here what it is saying that this is the error for a given X. What is the expected value for all X? So for this, for example, this is a function, this is a function, this is my hx, and for this X, this is the error. For this X, this is the error. What is the expected value? What is the error? What is this Ex saying? It is saying what is the expected value for all X. So this is my error, right? This is all my error. This is all my error. So on an average, what is the error for X? So let's say there are three x1, x2, and x3. And for x1 error is 1, x2 error is 2, and x3 error is 1. So expected error for X is 1 plus 2 plus 1 divided by 3. So it will be 3, 4 divided by 3. Right? This is expected. So this is on an average, what is the error for Ex? When I say what is the expected value corresponding to D, it means one by one I am considering different data sets. I am calculating the expected value X for each data set, and finally when I get expected error for each data set, I will average them at last. So just to write it for you, so for an example, for D1 data set, I get expected error, let's say 3. For D2 data set, I get expected error Ex equals to 3. For D2 data set, I get Ex equals to 4. Or for D3 data set, I get expected value of Ex equals to 2. Now, on an average for a data set, what is the expected value for X? That is what I'm calculating here. Let's go through these expressions. You will get a better idea. Because these are just expected value, expected value for positive values. I can interchange them. I've just interchanged them. Ed goes outside, Ex gets inside. So expected value of expected value, you can change it. It will not affect. For example, if you are doing integration, and this is X and this is Y, and you're doing integration of fx, y, dx, and dy, right? You can do like this, dy dx. So if you swap this value, change dy and if you interchange the integration, that will not affect the value of this. I know, I hope that you understand this from the calculus. So because expected value is again the integration from the part, and this is a positive integration, we can swap it. So this Ex goes outside, Ed gets inside. Now this is the expected value for the data, and this is this expression. I will because this is a square formula. This is X plus Y square formula. I open it, X square plus Y square plus 2xy. So this is first term, this is second term, and this is a square of it. When we opened it, it is like gdx square plus fx square minus 2 gdx fx. So this formula is like this: gdx square plus fx square minus 2 gdx fx, right? And this expected value, because this expected value is a linear, you can if you have two random variables x plus y, x plus y. So if you have two random variables x plus y and these are linearly combined, so you can write ex plus ey. This is a rule of sum of expectation rule. So now because this is expected of d, you can go one by one over it. So you have written ed of this, ed of this. But if you take constant value, expected constant value, for an example, every time you have 2 2 2 2, and you are taking the expected value of all these variables. So these are 2 2 2 2 and divided by the number of times 2 plus 2 plus 2 plus 2 and 1 2 3 4 5. So what is this? 1 2 3 4 5, so it will be 2 again. So because the value of a constant, expected value of a constant will be the value again. So ed of fx is constant in respect of ed, so it will same again. This is constant, it will get outside. So this is the expression here. When fx is constant, 2 is constant, so 2 comes outside of ed, fx comes out of ed, and this ed will on this expected value contain gd of x, right? What is ed? What is this ed gd of x? Let's understand this first. This is the average function. As I told you, you have generated many data sets. For example, you have 100 data points, a population, and at a time you draw 2 points only. So you can have these many data sets, 100 C2. So D1, D2, DK, and you applied some learning algorithm, and you got G1 hypothesis, G2 hypothesis, and GK hypothesis. For each data set, you get some hypothesis. What you are doing now, for each value of x, now for example, let's say this is the value of x, and you get first hypothesis, second hypothesis, third hypothesis, fourth hypothesis. What you are doing for this value of x, you are adding this number, this number, this number plus this number, and dividing by 4, because these are fourth hypothesis. On an average, you will get what is the average value for this x from all the hypotheses. What is this ed of x? Means to say, for every data set you have a hypothesis, and on an average, what is the value you get from all those hypotheses? That is what this average function is saying, and what this ed is saying. Ed means expected value of the hypothesis for a given x in respect to a data. Okay, I think so same kind of, please, what is fx again? We could sum for the same. I do not get this question. Okay, so we can now rewrite this expected out of sample error like this. This is same, right? From the previous slide. This is same. So now this ed of this, we have written like this. We just change the notation, nothing else. Expected value of the x given for a different data sets, that is given by average hypothesis. So this is replaced here, and we have just added minus g of x and plus g of x. They can cancel. You can cancel each these things because this is minus and this is plus, right? It will not change anything. Now this is a sum of a square formula. A square plus b square minus 2ab. So you are doing this square here. You are making the sum of this whole square. And because this gx is a constant in terms of this d, you can bring it inside and you can write this expression as like this. Now finally you express this sum of squares into two notations. You express this sum of square into two notations, that is this square and this square. This square plus this square. This how you can express it. You have expressed these things into these two notations. This is a bias. We call this as a bias, and this is a variance. Let's understand with the example of these. For an example, we have let's say we have a sine function. We have a sine function, and at a time we can draw consider a target function fx is equal to sine x. So this is a sine x function. We are considering only those x which are between -1 and +1, right? -1 and +1. To generate a data set x1, x2 and fit the data using one of the two models. So let's say we have two hypotheses, h0 and h1. Every time we take two data points from this function, sine function, 2 points at a time, and we try to fit the model one by one. First we try to fit the h0 and then we try to fit the h1. Hg is a constant hypothesis. I will give you 2 point. If I will give you a 2 point, then you just add those 2 points and divide it by 2. For an example, if I give you this point and this 2 point, and what I will ask you, what is the best line you can fit for these two data points, then this will a line always go through the mid of this. So this is what h0 is, and h1 is the line that always pass through the 2 points. So there are two models. We are trying to fit these two models using only two data points, and those two data points are generated from sine function. So when we do these things million of times, for an example, at a time I take these two x's, I got this line. Again I take these two x's, I got this line. I take these two x's, I got this line. So for every two x's, I will get different lines. So these lines are shown here. Million of lines are there for every two data points. Million of lines are there. When you take all these, now you take one x, add these values, all these values, and divide by the number of hypotheses you have. For example, these are 100 hypotheses. 100 lines are there. 1, 2, 3, 4, 500 lines are there. So you will get 100 values of x here, right? You add all these values and divide it by 100. You will get this value. On an average, what is the value that you are getting is this. That is what I told you. This is ED of GX. Right? What how did we represent it? Okay. Right. ED of GD of X. Sorry. GD of X. It is nothing but average of. Right. So this is this thing on an average. And what the variance is? The variance is because these are if you take any x and you will get this value, this value, this value. So you are subtracting the average of these values from the mean. So this is mean, right? This is mean. Now you are getting this is a mean, and you know how to calculate the variance. You are subtracting the value of x from the mean and squaring it. This is the mean you got, right? And you are taking every time one by one hypothesis and subtracting from the mean and squaring it and taking the average value. Average value means nothing, the variance of it. This is a formula of variance. So when I take the value, when I calculated the variance for this given x, when I calculated the variance of this given x, I I get this value because variance is square, so it is in both direction. For an example, this point is, let's say, point 3, let's say. So now variance from mean vary from -3 to +3. That's why this whole region is shaded as a black. So variance is +3 to -3, and this is the more restrictive model, H0. H0 is a more restrictive model because I have a 0 degree freedom. I can have a constant line. But when I increase the degree of freedom from H0 to H1, now I can have any line in any direction, right? Now what I get, the mean is very close to the true function in respect to H0. See the error here. The error here that I am getting, the average value, average hypothesis is, the error here is this. The error here is this. All this is the error here. And the error here is this. So you can see when I increase the degree of freedom, my expected error decreases. My expected error decreases. I told you in this previous graph how I calculated this expected error. I take this value of x and add all the values of x, these, and divided by the number of hypotheses, I get this point. So when I increase my degree of freedom, my expected error or my average hypothesis will be very close to the true function or more close to the true function. But here you can observe that the variance explodes in respect to this graph. When I was having a variance here very less, I am getting a variance very large here from this value to this value, right? So as you increase the degree of freedom, you get less biased. What is a bias here? This is the error that you are deviating from the average hypothesis. You get less biased. It means that the function you are using to represent the true model, true function, is close or more or can do good approximation for the true function. But the variance explodes as the degree of freedom goes high. But when that degree of freedom is less, when the degree of freedom is less, okay, so that's all in this, and I hope you can go through this, and we will continue it with, we will have a discussion over it. This is nothing more than that. Okay, thank you for that.